Welcome to the Explainer. Have you ever stopped to think about what really makes the wind blow? Or how something as simple as a gentle breeze can escalate into a monstrous, destructive cyclone? Well, today, that's exactly what we're going to break down. We're diving deep into the invisible forces that literally shape our weather.
So here's our game plan. We're going to connect the dots in 4 simple steps. We'll kick things off with the absolute basics, pressure. Then we'll see how that creates wind. From there, we'll look at the recipe for a thunderstorm. And finally, we'll scale it all the way up to the biggest storms on Earth, cyclones.
All right, let's jump right in. We're starting with a force that is all around us, pushing on us from every direction, every second of the day. And yet, it's completely invisible. We're talking about pressure.
So you have to wonder, the air above us actually has weight, a lot of it. There's a huge column of air stretching miles up, sitting on top of your head right now. So why aren't we all just, squashed flat?
And make no mistake, that weight is massive. Over a small patch about the size of your hand, the force is like having a 225-kilogram weight just sitting there. The reason it doesn't crush us is actually pretty amazing. It's a perfect balancing act. The pressure inside our bodies is pushing outwards with the exact same force that the atmosphere is pushing in. We're in perfect equilibrium.
Now, to get a really good handle on this idea, think about a heavy backpack. You know how one with really thin, narrow straps can seriously dig into your shoulders and hurt? But a bag with nice, wide straps is way more comfortable, even if it's carrying the exact same weight. That feeling? That's pressure. And here's why. Pressure isn't just about force. It's about how much force is packed into a certain area. Those skinny straps concentrate all that weight onto a tiny little spot, creating really high, painful pressure. The wide straps, they spread that exact same force over a much bigger area, which lowers the pressure and makes it feel a whole lot better. Keep this idea in mind. It's the key to everything else we're going to talk about.
Okay, so we've got the basics of pressure down. Now, let's see how that concept scales up from a backpack to something we experience every single day: wind.
Because at its heart, that's all wind really is. It's just air on the move. And it always moves from an area of high pressure to an area of low pressure. Nature is constantly trying to even things out. It's just like when you let the air out of a balloon. The high-pressure air inside rushes out to the lower pressure around it. That rush, that's wind. And you can see this play out perfectly at the coast. During the day, the land heats up way faster than the water. That hot air rises, creating a low-pressure zone. So what happens? The cooler, higher-pressure air over the ocean rushes in to take its place. That's your classic sea breeze. Then, at night, the whole process flips. The land cools down faster, creating high pressure, and the wind blows from the land out to the sea. It's a daily dance, driven purely by pressure.
Okay, but what happens when that wind starts moving really, really fast? Now, this is where things get a little weird, and it kind of goes against your intuition. You'd probably think that faster-moving air would create more pressure, right? But it's actually the complete opposite.
Check this out. It's a super simple experiment you can even try yourself. If you hang 2 balloons next to each other and blow a fast stream of air right between them, they don't get pushed apart. They actually get sucked together. The reason is that the fast-moving air you're blowing creates a little channel of low pressure, and the normal higher-pressure air on the outside of the balloons pushes them inward. So this reveals a fundamental rule of our weather. High-speed winds and low air pressure go hand in hand. The faster the air moves, the lower the pressure becomes, and that one simple fact has some seriously dramatic consequences.
For instance, this is exactly why roofs get torn off houses during a hurricane. It's not just the wind pushing it sideways. When you have incredibly high-speed winds screaming over the top of a roof, it creates an area of intense low pressure up there. Meanwhile, the air trapped inside the house is just sitting there at a much higher pressure. That pressure difference creates a massive upward force that literally lifts the roof right off the house.
All right, quick recap. We know that pressure differences create wind, and we know that fast winds create even lower pressure. Now let's take those 2 key ingredients and see how they combine to cook up a thunderstorm. So here's the recipe. It all starts when the sun heats the ground. That hot ground then warms up the air right above it. Now, warm air is lighter, less dense, so it starts to rise, leaving behind a pocket of low pressure. Well, nature doesn't like a vacuum, so cooler, denser air from the surroundings rushes in to fill that space. And then that air gets heated up and starts to rise too. You get this powerful, self-sustaining upward current of warm, moist air that builds into a towering cloud.
Now, inside these massive storm clouds, it is absolute chaos. It's like a giant, violent washing machine.
You have powerful updrafts carrying warm air up and downdrafts sending cool air down, and it's all just churning water droplets and ice particles, smashing them into each other.
All that friction and collision builds up an enormous amount of static electricity, just like when you drag your feet across a carpet. The cloud's charges separate, with positive usually going to the top and negative to the bottom. For a while, the air itself acts as an insulator, keeping them apart. But eventually, the electrical charge becomes so huge that the air just can't hold it back anymore. And zap! You get a massive, sudden discharge of electricity to balance things out. That's lightning. And that flash is unbelievably hot, hotter than the surface of the sun, which causes the air around it to expand explosively. That resulting shockwave is what we hear as thunder.
Okay, so we've built a thunderstorm. But sometimes, under just the right set of conditions, that thunderstorm engine can keep revving up, spiraling into the largest and most powerful type of storm on the entire planet, a cyclone. So how does a storm make that leap? How does it transform into one of these monsters? It all comes down to a powerful, self-sustaining feedback loop, a cycle that just keeps feeding on itself. And here is the secret ingredient. Remember all that warm, moist air rising? When that water vapor condenses and turns back into liquid rain, it actually releases a tremendous amount of heat. This released heat acts like pouring fuel on the fire. It warms the surrounding air even more, which makes it rise even faster. A faster updraft creates an even lower pressure center. That lower pressure sucks in more air, which rises, condenses, and releases more heat, and the whole engine just spins up faster and faster and faster.
And then there's one final piece of the puzzle. The Earth itself is spinning. So as all that air rushes in toward that intense low-pressure center, the planet's rotation gives it a little nudge, a twist. And that twist is what organizes the chaotic storm into that classic, massive, rotating cyclone, complete with that famously calm, clear eye right in the middle.
And the impact of these storms is just devastating. The wind speeds are incredible, faster than a high-speed train. But often, the most dangerous part is the storm surge. The combination of the intense low pressure and the powerful winds literally pulls the ocean's surface upward and pushes a massive wall of water onto the shore, sometimes 3 to 12 meters high. It causes catastrophic flooding far inland.
Now, the good news in all of this is our growing ability to predict and track these monsters. Thanks to weather satellites and dedicated organizations around the world, we can often see these storms forming days in advance. That gives crucial warning time for evacuations and preparations, which saves countless lives.
And that leaves us with one final thought to chew on. We've seen that the Earth's spin is the essential ingredient that organizes a chaotic storm into a rotating cyclone. So if our planet were to suddenly just stand still, could these ultimate storms even exist? Something to think about. Thanks for watching.